why there's. I'm going to share my screen. Only me participating so far. Okay. I think I was pretty close to just beyond that one. We talked about that. You know, and it's still in the two-dimensional now.
We have a golf simulator.
On your computer and
No,
campus.
like, on campus at the rec, they have a golf simulator.
Oh.
I had no idea about it. I think, yeah, I think so. We should check it out.
Yeah, I'm good with that.
Talking about the nanocomposites of the clubs,
Yeah, exactly, yeah.
right? Carbon fibers.
Yeah, carbon fibers are macroscopic.
Senior clubs are graphite shafts.
Again, macroscopic.
They can get nano graphite.
All right, still nobody online, that's okay. Hello. Welcome.
You said if you're taking attendance, just work.
No, I'm not. If you're here, you're here. Everybody's been there in class, so I count to 7 and I'm done, so. I do have a barcode, I mean, a QR code I use for larger classes, but I can tell when all of it. Okay, I'll give them a minute or two here. So I have, I'm going to do 2 more things with the book kind of as it's structured in part 1. So I'm going to go on to, after the describing of these, I'm also going to go on to resin selection, which is chapter 4 or 3, resin selection and processing. But then I want to break it down and look more deeply into each kind of thing you would do. For example, the first thing I'm going to do is mechanical properties, specifically looking at the modulus, tensile strength, elongation, and impact improvements. But then I'm going to go on to a different topic of electrical conductivity, electrical resistivity, thermal conductivity, thermal and electrical, and I'm going to break them down into use cases. And in each of those use cases, we're going to do a material selection and why you would select that material, processing, and how you would analyze, because they have different analysis techniques. So we're going to start with the mechanical because that's easiest, because you look at your stress strain curve, that tells you a whole bunch of information, but that tells you one kind of information about tensile strength and tensile modulus. But then you're going to have to look at flexural strength and impact properties. Impact properties is different; it's a different time regime, so we have to use a different kind of testing. And so that's what I'm planning to do. And it will start after chapter 3 in the book, which is technically the second half of the book, but I'm going to start with mechanical. And so there's going to be more words on the slides. Let's put it that way. So anyway, I think we can start because we're all here more or less. So we were talking about the different types, and we'd already gone through one-dimensional, which is the plates. Huh? I am. I forgot to record last time. I am recording now. Thank you. Yes. So that one did not get posted, and of course we missed one of those lectures. due to, oh, we didn't miss a lecture, did we? We had to go home and find, I just, yeah, I was sick as a dog on Thursday and Friday, I don't know why. I'm better now. Okay, so now we've moved on to the two-dimensional, which we have two axes that are in there. And typically there's a very long axis outside of the narrow range that goes for those fibers. And they affect the length of those fibers gives you different properties, okay? Like let's say you have a long conductive multi-walled carbon nanotube, right? That is going to give you a different level of loading required to get a desired change in electrical conductivity in a shorter length. So that macroscopic dimension still is important. Okay, so in the multi-walls, you're more likely to get a higher conductivity per bundle of them because you have more places to run current through. But that longer length you have is going to help you with your properties. And that goes into a concept called percolation threshold, which we'll discuss separately when we talk about electrical conductivity. So in these nanotubes, you know, we started with the carbon nanotubes and said that they were single and multi-wall and they have different properties. And now we're going to move on a little bit to some of the ones that are multi-walled carbon nanotubes, I'm not sorry, out of carbon nanotubes and into the ceramic-based nanotubes. And so it's going to be similar to that of the clays, except instead of having it so they're all flat and perfect with the bilayer of the aluminosilicate, there's actually defects in one of the sides and you end up getting it to curl. And so it'll curl and even and many times spiral to give you that. So it's technically an aluminosilicate just as the 1D stuff is, but instead of being flat plates, it rolls into spirals, and those spirals end up being two-dimensional across the diameter, but they tend to be more macroscopic across there. Now, because of this, there's less interfacial surface area between the clay and the clay on the two different nanotubes, and they're much easier to disperse. In the plates, you have to shear away, shear and get stuff in between all those plates to break up the plate-to-plate interaction. In the nanowalls, there's only a minimal contact between them, and they're much easier to disperse. And so you can get a grade of naturally occurring one, specifically called halloysite, which you can just shake it in a glass of water and it will go in very quickly. So because of the difference in interfacial strength here, we see that it'll disperse more easily than it has, and it has a less effect on the viscosity of our system. But again, it's what property you're going to look for. This is going to do well for mechanical strengthening because you have the very long axis and you have the very small diameter here in the nanoscale. So you're going to get lots of inclusion and lots of macro domains associated with those long ends of the fibers. But if you're trying to get some other thing like an impact or a barrier resistance, the tubes aren't going to do you any good because it's just going to go around the tubes. So again, choosing the right material for property is going to become important in our next 3 chapters that we go on to. So in this system right here, we end up with, technically, you almost never see a single wall, but they kind of spiral up together. And so they have varying diameters of these tubes here and varying wall thicknesses, but most of them tend to be hollow because there's at least one layer of the defect that has to make a full circle before it starts growing around the outside of that. So you tend to have a small hollow center, usually between 10 and 50 nanometers, and then the walls tend to be vary depending on where you actually get your nanotube, or if it's synthetically made, you can make them synthetically as well. So what we'll see here is just like in the carbon nanotubes, which are hollow, these type of aluminosilicate nanotubes can also be hollow. But unlike nanofibers, carbon nanofibers, which are not hollow, these tend to be until we get to the fibers of metal oxides, and we'll talk about that separately. Okay, questions on that? Okay, so being that that has a slightly different morphology, turns out depending on the macroscopic length of your system, it'll change your properties even more. And because they are easier to disperse, we actually get a much better dispersion that we see in this, and I believe this is nylon, where you have at even very high loadings, you can have your tactoids breaking apart, giving you individual tubes that are dispersible here. But then even at this really high loading you see on this side here, it doesn't change the viscosity so much you can't process it. So the fact is that you have only the one long axis, the two small axis, lowers the viscosity problems, and you actually get a better dispersion with lower shear processing. Okay, does that make sense why we can have lower shear processing from this system? Because less of an interaction between the inner surfaces of themselves, and they easily disperse, and now they're interacting with the polymer matrix itself. Okay. So when we move on from that, we can actually go on to the next one, which is actually solid metal fibrils. And these are nickel. And you can also do silver, aluminum, other things. Nickel and silver are probably the two most common. Nickel is the most widely used because of its corrosion resistance. Okay, silver oxidizes in air. It also has a certain photoactivity associated with it. So it's used in processes where you're looking for very high conductivity for electrical and thermal, but it oxidizes over time and oxidizes at the interface. The nickel, while it doesn't have as high electrical or thermal conductivity as the aluminum, as the silver, it does have much better environmental stability. So you can take these materials, process them in your polymers, and then even pyrolyze the polymer out to get this porous microstructure or nanostructure. But notice that they aren't perfect wires. They're not like the tubes we saw in the other system. It's globs of that. And if you're thinking about it, it's not amorphous silicon. These are little crystals that are kind of growing crystal faces on crystal faces. Okay, so this isn't a pure, ductile wire. It's actually the little crystals that are kind of bound together. And when you process it that way, in fact, I think you can even see crystal faces on this, they have a certain amount of strength associated with it, but their properties really rely on the metallic nature of these. So we're looking at electrical, EM, shielding, and three-dimensional electrical and structural increases using this material. So you could almost say this is really a 0D material. They're just kind of strung together in little crystal facets. But technically under the book, it's a two-dimensional because the individual crystals are smaller than the 100 nanometer, but the length, the aspect ratio of the total length of the fiber is high enough to be a two-dimensional material. All right, questions on two-dimensional, because I think we're moving on to three-dimensional next.
I have a question.
Yes. No.
That's specific to air.
Uh-huh.
That's more like, would that look more like macroscopically? That's still like a bulk material, right? It doesn't look much like a composite. How would you?
Well, okay, so what you see here is this is where it would be in the actual composite, where it's dispersed into a polymer matrix. This is if you process it so you burn out the polymer matrix so you can actually look like a three-dimensional structure flux. Okay, and so that is kind of more where you have this right here. Now, you can do that a couple different ways. I've done it with just rastering the SEM. Crank up the voltage on your SEM, raster it out. You have a polymer that'll blow off. You can etch down a couple nanometers and get this three-dimensional structure. But a lot of them do it either by thermal evolution or through sintering processes. You got to be careful about sintering processes because nanomaterials have lower melting points than their bulk property. So, if you try to say, oh, I have the structure, I'm just going to melt the polymer on at 200 degrees C. No, that might be the melting point of your nanocrystals, and they'll just kind of all fuse together. So, but we can see that, and so that's what these two images are. But you can see that it's dispersed in a matrix. Okay, that answer the question. So the next one we want to talk about are solid fibers, not hollow, solid fibers that are also oxides. And so this particular one is a aluminum oxide fiber, and it's made synthetically. It's made synthetically along an oriented axis. and they are solid, they are not hollow, and so that when they make, they're also crystalline, like almost 100% crystalline. Just kind of like your carbon nanotubes are kind of grown off a particle, these are grown off a surface, and so they're grown almost in a perfect crystal length. The actual fibers themselves can be broken off because, again, the interfacial, the crystals are the strength of the system. The actual interface from crystal to crystal is very poor, and therefore they're easily exfoliated by lower shear materials. And in the case of here, you can actually see that, you know, it's grown axially like this, and the fibers, bundles, are really nearly perfect. And then as you mechanically abrade them off, they can be dispersed into your matrix, either by melt or solution. But they are crystalline all the way through, and they are solid all the way through. So that's a big difference. So now we're going to look at something that we haven't talked about: density. Hollow tubes can be less dense than solid tubes. Hollow tubes can be just as strong as solid tubes because of the cylindrical structure. Solid tubes might have higher conductivity for thermal or electrical purposes. So again, application, cost, benefit to cost to benefit ratio. That's what we're going to start talking about in chapter 3, and then each individual type. Okay. So again, these are processed a little bit differently. This particular one is actually used as an anti-abrasion, anti-corrosion coating. You can mix it, disperse it with a low viscosity polyether, and then coat it to give it a coating on aluminum structures in particular. So imagine you already have aluminum. As soon as you abrade it, you got an aluminum coating on the top, right? It's going to automatically form that oxide. Well, that oxide can be fairly dense or not, depending. But now you're putting a very dense crystalline fiber in a matrix right on top of that aluminum to help it basically bind the native aluminum oxide layer with the fibrous aluminum oxide to create a strong corrosion resistant and tribological smoother coating. It's less wearing. Aluminum, if you know anything about aluminum, it galls quite a bit. It's easy to smear it. And so by having this slightly harder layer of oxide on the surface, anodizing is one way to do it, but you can do it in a nanostructured coating with this, and it'll still give you some better, less galling effects and less corrosion effects from motion. All right, questions on that? Okay. All right, so now let's talk about our three-dimensional materials. So remember, in our three-dimensional materials, we can't just have individual atoms because they're too small or not in the 1 nanometer range. We can have clusters of atoms, and those clusters of atoms can be amorphous or they can be crystalline, depending on how we have them. So the first one I want to talk about is kind of an organic one, and it's kind of an organic one because of the things hanging off it. The sesquilane cages here, the cage itself is just above 1 nanometer, okay? But there's a whole bunch of these different resins made with this, and by changing the R group on here, you can make it compatible, you can make it reactive, it can be its own nano composite resin. You can polymerize the ends of these things and it becomes its own nanocomposite resin. So that's one of the benefits of this system here. And there's an entire catalog of these materials, from hybrid plastics, everything from methyls that are practically insoluble, but they're very durable, to having 8 different functional groups on there, so that you can zip things up and turn them into hydrogels, which is what I do. Okay, so if we look at what that kind of looks like, why is it nanocomposite? We see that these right here are a volumizing bulking agent. Okay, so if you want a nanocomposite that says, oh, I want to actually have selective gas permeability. Selective gas permeability means you want a certain amount of free volume in your system, and you want to have it consistently all the way through your polymer so that your gas diffuses, your gas of choice diffuses at a specific rate and slows or speeds up everything else. And you end up getting just one gas. And the way that happens is because you can polymerize not only one side, but multiple sides, you can get these free volume areas in your polymer matrix. The polymer matrix tends to be less structured and have a lot more flexibility at room temperature. And so you can get the gases permeate there, but having that free volume to hold those structures. Having the spheres, the spherical things holding those things makes it easier to have that process. The other thing it does is it bulks it up with not changing the viscosity significantly. Okay, when we were looking at montmorillonite, the plates, that changes your viscosity significantly. The fibers, depending on the aspect ratio, can change your viscosity. This does a little bit less of a job of changing viscosity because the actual part is part of the matrix, part of the polymer you're actually using. Okay, so
Can I ask a question?
yes.
So free volume, that only refers to the polymer, right? Like if there's a particle that does not, that volume is free, or what, can you describe that?
Free volume, what I mean by free volume in this is the effective permeative density. Okay, so if you, let's say you had a polymer that was just the polyacrylic acid or polymethacrylate right here. Okay, polymethacrylate, its effective density can be close to a little over 1. And so its effective free volume is based on just the polymer. Because of creating this freer volume, and this is a less dense space, it's going to give us, these can't pack together as tightly as a polymer without them on it. If they can't pack as tightly together, our density goes down and our effective free volume goes up. Does that make sense? So it also changes our liquid permeability problems as well. Let's see. Okay, so, but just like with the other things, compatibility seems to be a problem. In this, if you have something where the side chains are not very compatible with your matrix, you will get precipitation of your particle, technically your nanoparticle, your three-dimensional nanoparticle. So in this case here, when we have just the cyclopencil groups on the side here, that makes it very rigid, very crystalline, and not wanting to go into too many polystyrene. Okay, polystyrene, it's fairly large, rotational, where the rings are kind of on the outside. It has a large coil structure to it. This just doesn't have a good compatibility with it, and even at fairly low loadings, you'll see that it precipitates out a solution, forming very crystalline regimes. Now, by taking that out and adding styrene to it, hey, polystyrene should dissolve in styrene, right? Well, again, we have the styrene, and there's 8 of these hanging out there. Yes, that would be very compatible with the monomer. In fact, it probably dissolves very well in the styrene monomer, but the polymer actually doesn't have the double bond and the rigidity that the styrene has. So let's space that out a little bit more, and instead of having all styrenes have just a few styrenes, well, that helps a little bit, that doesn't take it all away. What if we take it and change that compatibilizing group to be exactly like polystyrene is once it's polymerized? It takes away the double bond. So basically you have ethyl benzene. And if we go to that scheme here, we take out the double bond, add the flexibility that we see on the polymer chain, we can get 58% with no formation of crystallites from that system. So this is probably a first example about how compatibilization with our surface on our polymer, on our particle or our nanomaterial has a huge effect on its ability to be used for its intended. Okay. So just to remind you, polystyrene has no double bonds in it once it's polymerized along the main chain, and gets that coil from the fact that these are butting up to each other. All right. So moving on from here, this is one of the few that's kind of almost a molecular or semi-organic material here. The rest of them are going to be closer to oxides, metal oxides or metalloid oxides. And the first one we're going to talk about is silica. So silica is silicon dioxide, or some morphology thereof. It comes in 2 forms, amorphous and crystalline. Okay, so amorphous tends to be The first one's made, and they tend to be made through a thermal, either hydro process or a vapor process, where you basically burn silicon tetrachloride in a wet flame, basically, and it produces what we call fumed silica, nano-structured amorphous silica, SiO2. And with the different grades, you can get different structures, overall structures, both macroscopic and microscopic structures of this. And these can be dispersed very well in things that hydrogen bond or things with low viscosity. But because of their surface area and their surface energy, they can have a huge effect on the thickening of your solution. So if we go to an example, I believe, yeah, wait, I have a graph here. If you just have your fumed silica as not made, it has, a carbon content of 3 to 5%. It's got a lot of a little bit of ACL still on the surface. And so it's got a lot of surface energy. And so if you don't modify that surface and try to blend it into your material, the viscosity rise after about 10 or 15%. It's really high. In fact, you can go, it's even added for a lot of paints and oils and greases and stuff to actually have a low loading and affect that. However, if you change the surface area enough, or you change the surface area and the surface energy, you can actually get the dispersed system. Now, in that monodispersed system, what they've actually done is they've taken the nanoparticles, the amorphous nanoparticles, and aggregated them together chemically. When you aggregate them together, they are still individually nanoparticles and they can be dispersed. But the clump moves as a single unit, and therefore does not have, you can have still the same number of particles dispersed in your solution, but you have a fewer number of aggregates or tactoids. The fewer number of aggregates or tactoids lowers the net viscosity. So you can get it into process, and then at the final stage, when you do your final processing, you can disperse them. Okay, so that means that these are going to disperse into your liquid, and then in your final process, when your polymer or whatever grows in between them, they'll break them apart, and you get very well dispersed nanomaterials. Okay, so it's a trick to where you want them to be nanoparticles, but you want them to act like a big particle until your final processing step. Then you have them break apart back into your nanoparticle. Very clever, and it works mostly, I think it only works with silicon and aluminum, alumina and silica. Okay, so let's see. Okay, and so there's the effect of that. Okay, so now we're going to move to part 3 right here, and we're going to get into the other oxides. And again, the oxides, all of these three-dimensional materials are all not hollow. The closest one that's hollow is the POS, where it has some empty low density area, but all of these are going to be solids, and they're going to be either crystalline or amorphous, depending on which grade you have. This particular grade right here, it looks crystalline, but it's made by a similar process. They actually started this back in the 50s. You can make aluminum chloride and actually do a hydrothermal version or a flame version, and it produces the same level of, in this case, the flame versions produce low crystallinity, almost amorphous aluminum oxide, and can be used. So what do you care if it's silicon dioxide or aluminum dioxide where you're going to do it? Well, they'll have different compatibilities and different long-term effects on like UV stability and all these things. So you can choose whichever one you want. And the silicon is actually cheaper. So most people go for the silicon, but the aluminum oxide is slightly more dense. So there's a trade-off there. So once you go to that, you can get them in a wide variety of things. Most of these silica and aluminum nanoparticles are made through a flame process or a hydrothermal process. So they are taking it and heating it up with water under pressure, and then it either creates a Amorphous, which is the spray version, usually creates amorphous because of the time scale. The hydrothermal process tends to make more crystalline materials because it has more time to form. But then once you have that, you are going to do the same kind of thing you would do with graphite, in the fact that you take raw graphite, which is a bunch of little sections of platelets, grind that up till you get to smaller sections that are tectoids, and then you can process them from there. So in the case of this, you can have amorphous powders, which are used as anti-caking agents, as things that are on surfaces, etc. Or you can have them as particles. And then particle distribution can range anywhere from macroscopic to nanoscopic based on what you want. Sometimes you want your silica gel packs to absorb water. Sometimes you want a really high surface area and you want them to be very small particles. But then you also have a crystallite form, and it's like 80 to 90% crystalline, but it can have a little bit of difference because there can be some internal volume in between the crystallites. And so you got to start thinking about pore size, what will fit in there, what won't fit in there. So if you're thinking about nanostructured materials like zeolites, they have specific pore structures. They technically are a macroscopic particle, but they have nanoporous structure. Here we're actually taking the polymer to make the nanostructure, the nanoparticle to make the nanostructure. All right, let's see. So, and most of the time, we can't really get them from macroscopic to nanoscopic mechanically. So we can, through cryo grinding or other ways, go from our macroscopic particles down to small conglomerates. Then technically you need some other process that will take it down. So typically you would use something more on the lines of not cryo grinding, sonification or something that will break them apart again. Because what we're trying to do is we have to break the energy between the little substations to whatever the matrix is. So this mechanical process or chemical process is done with your matrix or your compatibility. So you can get down to here with just mechanical and air. Once you get to lower than that, you can do it mechanically, but you have to have something that's going to stay in between the particles. So that way you can do, might be able to do cryo grinding because the frozen, the liquid is going to stay between the particles. But most of the time you're doing it here, you're actually grinding or processing it at last a little bit with your matrix or some kind of matrix compatibility. So that will get you to those dispersions. And again, they have very good chemical resistivity, just like silica and alumina both have very high chemical stability for that. And thermal stability. Okay. So this right here is SEM of, you can see they're crystallites. They're crystallites of aluminum oxide that have been dispersed in nylon. And these have been dispersed in nylon through extrusion. So it started with a macroscopic powder that went into the extruder, and then as it got through the shear, the polymer was in between the different particles as they mechanically sheared. They didn't have the opportunity to recoalesce because the polymer then got to that dispersion. But again, notice the irregular shape of these crystallites. Okay, so we don't have spheres. We don't have long aspect tubes. We don't have plates. We have these really rugged, sharp crystalline regimes. And that's going to change our properties. Just like you need sharp sand in concrete to get mechanical bite, this is going to have a different process than a spherical powder. So we'll see that in the effect of tensile strength. All right, questions? Okay, so again, any of the metal oxides can be made this way. Titanium oxide is used a lot specifically for reactive surfaces. It actually has a photoactive effect that you can use on there, photooxidative effect. And it has a slightly higher density than the other ones here. In the case of silver, we can get nanocolloidal silver that is 100% metal in the center, mostly crystalline in the center, but then we'll have some kind of surface. It's either gonna have a surface oxide or it's gonna have a surface modifier that keeps it from having an oxide. And that would be things like carboxylic acids and something like that, where we have this chemical modification to keep them, number one, dispersed, number one, keep them the size we want, okay? So if you make a 40 nanometer silver nanoparticle and then your solution completely dries out without something in between those particles, you now have regular old silver. So you want to make sure that you have the one you want and it stays there and it stays compatibilized. And just like in the gold, they change colors, their interaction with light changes with the particle size. But again, if you let this solution dry on a surface, you now have silver on the surface. You don't have nanoparticles if you heat them up at all, because they're going to aggregate. Okay, so that is where I want to actually stop with the nanomaterials. So we have 1, 2, and 3-dimensional nanomaterials. We're going to talk about how to choose a matrix and or particle mix to suit what you want. And then there's different processes on how we're going to do it. Okay, so this is technically chapter 3 in the book, right here. And I want to stop here and talk about topics that I plan on covering. Mechanical is the topic I want to cover next. It's not this one, it's the next one. Thermal, there's actually 2 thermals. There's thermal resistance, and then there's thermal conductivity. So you can add something to make it more resistant to transferred heat or less transferred heat. So I'll do actually both of those in thermal. Flammability is different. Flammability, you're going to use something like magnesium oxide, which suppresses smoke and keeps things from burning or gets a surface energy change. So flammability is different. I don't want to do ablation, even though we have a rocket motor room here on campus, and we've actually done ablation testing here using Nanocomposites, because I only know the one paper. Electrical, we actually can do 2 things too. You can make it higher or lower, and it's all about percolation threshold and your use right there. For example, if you only want 1 order of magnitude electrical conductivity change, you want a very low loading or very poor electrical conductor. You want to make it insulative to 5,000 volts. You're going to want to put some carbon, some nano, carbon, not carbon nitride. Silicon carbide, sorry, nanosilicon carbide. And then I can cover tribological. I don't know a bunch about tribological, but the one thing that's not listed in the book that I kind of wanted to do was diffusivity or permeation properties. Because you can do gas and liquid permeation, and you can change that with the different kinds of light, in particular, because it really works best with the plating. Any other topics we don't have that we want to? So I'm going to do permeation and not ablation and not tribological, but permeation.
About radiation shielding. Radiation shielding.
Radiation shielding as in EMI, electrical radiation shielding, or cosmic radiation shielding? Because most of the time when we talk about radiation shielding, we use a macroscopic process because you need bulk. You need heavy atoms and you need a lot of them. But I'll look and see if there's something about that. Radiation shielding. Radiation.
I just try to connect that using concrete tests.
Okay.
Why we are not using the radiation current test?
Okay, I don't know that much about it, which is why I don't want to cover it. If you want to, if anybody wants to give a talk on ablation as their thing, I would love to learn more about it. I know that it works by having a very hard material embedded in your matrix and it's blunting off as things go by. That's what I know about ablation. So if one of you wants to do that as a topic, But electrical, I've done a whole bunch of stuff on. Permeation, I've done a whole bunch of stuff on. Mechanical, and I'm doing flammability now, actually, as part of my system. I will look up radiation. I'm not sure. And then we were gonna, you were gonna do special concrete. You're gonna do concrete, or you want to do that as your special topic then?
Yes.
Okay. So I'll let you do that because again, I don't know much about nanocomposites and concrete. I know you need sharp sand. That's what I know. Concrete. So
I don't know if it's gonna be related or not, but we are using nowadays too much alkali activated materials in concrete cementitious materials.
Mhm.
So the effects of that nanomaterials to geopolymerization and polycondensation processes is gonna be related to our topics.
it can be. It depends on whether you are using the gelling agent or the surface to modify final properties, or does it act as the glue that sticks things together, or does it actually create a nano regime? Because if it's creating a nano regime in our system, then it fits into our topic.
It just creates a glue.
It just creates the glue.
That's behaving as a filler. It doesn't include our topic, as you said.
If you can find a paper on the nano, these are nanomaterials, I'd love to hear it.
Actually, if you will find something like nano, for example, there is a topic like nano silica modified sinus periods. Okay. So even in those topics, we don't go in detail like we are using like this type of polymer. It has these much bonds with it. Just like study if they are like the rheology is perfect and mechanical properties good or not. We don't go in detail about the polymer reaction with that respective nanomaterial. For example, if we are using the carbon fiber reinforced polymers and we're using another nanomaterial as well with it, we don't see the interaction between these two. We deal them separately.
Okay, so more of a holistic,
Yeah.
what's making this a better improvement than others.
Yeah.
I think I will touch on that when I talk about different applications. And you can definitely see compatibility differences from a mechanical point of view, from just aspect ratio, and from a surface absorption issue, like how the polymer interacts with the surface of the metal.
Yeah.
So those do affect final properties, and I think I can lead that into especially mechanical and electrical.
Okay, so what we'll do, we'll send you a bunch of different topics. From that, you
Yes.
can select for us.
Yes, please. Please. If I don't know much about them, I'm just going to sign them one. So I'm sorry. I mean, this book was written, not too long ago, and so it does have a lot of stuff about companies, and a lot of the companies have actually looked up is still in business or changed hands. So that definitely gives you a great reserve way to go look for these things right here. There's also a website I go to all the time. It's Nano. Basically, you can buy almost anything that you can buy Amorphous, this little mom and pop thing out in Houston. They'll just ship you back in the mail.
No more.
Nano.
Like a more than.
Like as in amorphous. But well, yeah, I guess it sounds like love too. But here, I'm gonna let me stop sharing for just a second here. Stop sharing. Bring up here. Let me double check. Because it's Nano. They also have great pictures of different materials. Of course, they all look the same. Nano should be, yeah, Nano. Nano is amorphous topics on the nano scale. They have oxides, they have metals, they have crystalline, they have amorphous, they have nanocrystalline. And you can get all the elements here. I don't have an account name anymore. Well, I probably do. But they also sell carbon nanotubes and carbon fibers of different diameters. And I mean, you know, I bet each one of these is used in a different commercial product because, you know, we got carboxylic acid modified multi-wall carbon nanotube short in length. And then we're talking about aspect ratios here. So, I mean, this book, you know, is basically going to direct you to this. And then we'll probably take a few papers and they'll say, well, I used exactly this and this, and these are the two properties I got in comparison between them. That's going to give us a little insight onto the compatibility between the matrix and the nanomaterial. So amine functionalized, graphene oxides, easily dispersible, all sorts of stuff.
Do we know where they source this from?
I believe they probably get them all from China now. Or research groups, any professors spun out a little company, they make 100 grams of it, they sell them 100 grams for $1,000. They sell it to us for $10,000. But no, but they're, I mean, they are amazing at the number of things you have here. The metals and the oxides are the ones where I used most of my stuff were no, I don't want to go in. But nano wires and rods, that's where we're going to see more things that are metals, 100% metal, silver, copper, etc. There we go. So this is my go-to when I was talking about nano pyrotechnics. Nano pyrotechnics. Pyro. Right here. Because what you do is you mix a metal that wants to be an oxide with an oxide that wants to be a metal. And boom, they switch over or release lots of energy. But you know, anything from like the copper oxide with aluminum powder. It's great. Iron oxide and aluminum powder. The smaller it is, the faster. So anyway, sorry, got distracted. But I mean, just on this right here, you can say, okay, well, I'm going to use the zirconium for ablation. I'm going to use the titanium for surface effect. I'm going to use a silicon carbide for thermal conductivity. I'm going to use the gold for electrical conductivity. You know, pick your particle, pick your property. That's what I love about this website. All right. Okay, sorry I didn't share that screen on the video, but you can find it. All right. All right, back to the thing at hand, which is the slides from chapter 3. Okay. So I alluded to this before about how you can get your materials processed into your system. And there's 3 things we have to pay attention to. The aspect ratio of your material. So whether it's 1D, 2D, 3D, because that's going to change how you process. 2, the property you want to get out and how you want to use it. Okay, why do I say how you want to use it? If you want to use this as a modifier on a silicon chip, that you want a certain, like a high voltage silicon carbide resistor on your silicon chip, you don't need very much of it. You can process it in solution. You can process it by some very high expensive property. But let's say you wanted to make your nylon flak jacket be EM shielding, and you want to incorporate carbon nanotubes. Are you going to do that with a solution process? No, you're going to try to do through extrusion or some high bulk volume process. Let's say you want to make a very sensitive Geiger counter, so you want to build a case out of ABS plastic that has some kind of material in there that will shield it from radiation. I'm just using that as an example. I don't know. They might do that. So knowing which way you want to process it is how much you're going to use. So that's why almost all of these, you see a whole bunch of nylon 6. Nylon 6, dirt cheap, and it has great surface energy. It's got a lot of hydrogen bonding. So it has great energy that goes onto the surface of your metal oxides, your plating clays with surface defects, because there is a certain charge on the surface. There's a certain negative charge on the surface, and so it binds to those really well. And we end up getting a very good compatibilization on a chemical, on an atomic level. But let's look at this right here, just with a single screw. We're not getting sheared, we're still having those tactoids, it's not breaking apart. And we're not getting exfoliation of the part. We might be crushing some of the larger clay particles down to tactoids, but you're not really getting very well processed. Then once you get to low shear, you can start to disperse it a little bit. This is counter rotating, and so they're rotating against each other right here. You're getting a little more shear, but it's not as high, it's much higher shear than this, and you can tell by the TER, right? Until you're getting smaller and smaller tactoids, they're getting smaller. Now let's go to a counter rotating with medium shear, and you're getting some of those tactoids broken up. You look at, you've got some individual plates here in the middle. Counter intermeshing medium shear. Okay, because counter rotating is where you have the blades kind of go across each other and they're creating a small zone in between, right there. But when you have it more like teeth grinding past each other, like a metal crusher, those are intermeshing sheets. In that intermeshing, you're getting a very high shear zone for a very small period of time. Very high shear zone breaks up your tactoids and lets the polymer eject itself in between those plates before they have a chance to go back. Yes.
We talked about this, but you remind me, like, is this like a heated process mixture to make sure it's
All extrusion processes are heated. You have to be at a temperature above the melting processing temperature of the polymer.
and how do you, when you cool it, how do you ensure that you don't lose structure if it's really fast?
Well, the nanostructure itself is controlled by the viscosity of the matrix. So let's say you had your thing in water. You stirred it up. The viscosity of water is 1. Settles out. Let's say you now process it in nylon. Your viscosity in nylon is 10,000 centipoise.
Right.
It has to have a long time to set it. Right. So really, in the time frame of most extrusion processes, you do cool it down relatively fast, but again, viscosity of the matrix is high enough not to set it.
Okay, and the viscosity changes with heat, right?
Yes.
Yes.
Yeah, there's some ranges that you can do. You have to have a minimum viscosity to get your pellets to melt, but then your shear might be too high, you might destroy your polymer. So you have to have a low enough shear, a high enough heat, so the polymer melts enough so that it's not destroyed by the shear, and it's not too high that you're thermally degrading it. In the case of this, where we have Oxide 15 actually is a quaternary ammonium salt modified natural clay. And so it's spacing the plates out already. And that quaternary ammonium salt, which is compatible with nylon, polyamide, nylon 6 here, it kind of dissolves into the matrix and the polymer takes its place. So the modifier on the nanoparticle is catalyzing with this salt. But we still had to have heat to get everything to move. We still had to have shear to get the tactoids to break apart and not the back. Now, if you were to take this right here, burn it out, and burn it out in a way such that it doesn't melt while you're doing it, you can actually get the 3-dimensional structure. But then as soon as you put a mechanical force on it, those platelets are going to go back down. So you can actually have these, like they're called, it's an inorganic aerogel, aeroclay, yeah. You can actually maintain that 3-dimensional structure through freeze drying or burning out or something like that. But with any mechanical force, they're going to want to go back to plate later on. Okay. But we don't see that in the polymer system because the polymers in the light. Okay. Neat. Okay. So what we can also see is there's an effect with the molecular weight, because molecular weight is going to change your viscosity at different temperatures. I'm assuming these are all made at the same temperature. Okay, so as we go from the high molecular weight to the medium molecular weight to the low molecular weight, we see that the only thing that should be changing here is the shear generated by the polymer. The higher molecular weight polymer should have a higher melt viscosity than the medium and low molecular weight. The polymer melt viscosity is controlling the shear. That's why in the top one here, we have very good dispersion. Here we have mostly good dispersion. Here we have tactoids. Our viscosity is decreasing as we're dispersing less and less. So the in this particular case, choosing a higher process temperature for this lower material would be important, or changing to a higher shear sheet to get the same level of dispersion. So, you know, if you've ever tried to buy nylon 6, you say, hey, I want some nylon 6. And the guy says, what kind? You go, well, you know, nylon 6. It's like, well, I got 7,000 grades, and you can get anywhere from a pound to 17 million pounds delivered tomorrow. Which one do you want? I don't know. But you run the experiment and say, oh, shear's too low. I need your next higher grade. So I did a permeation one where we did polyurethane. We used polyurethane and we wanted to get a montmorillonite clay to solve the polyurethane. Well, polyurethanes are very rubbery, okay, viscoelastic, but they have a pretty decent energy. And so what we were able to do is we were able to take them, do a single process where we took the big particles of clay, had it modified with quaternary ammonium salt, got it through the extruder once with just a co-rotating, did an okay job, but then we ran it through again with adding more polymer at a lower temperature. When we ran it through again, we've already got it dispersed to the first level of tactoids. We diluted it down and increased the shear. Diluting it down and increasing the shear dispersed it into the polyurethane. Okay, and so then you know, I went, hey, I need some polyurethane. So what you use?
This is thermoplastic.
Thermoplastic. It's thermoplastic polyurethane put through an extruder. We ended up making extruded films with it. I said, well, it's going to be used in the medical field. Oh, okay. So you have to choose one of these 75 medical grades. So we had to go and figure out, okay, give us a mid, a low, and a high viscosity in the melt, and we saw which one worked. Turned out the mid grade worked best for our material. It had the best elongation properties, the best permeation. But you know, you don't know until you try. But you have an opportunity to fix it if you do only have one size. You say, okay, more shear, run it through 2 more times, break up this thing. Okay, so, and if we look at this right here, we actually see a difference in the properties given. Now, in this case here, we're looking at the percent montmorillonite, and this is the elongation to break. Okay, so if we think about it, the lowest molecular weight polyamide is going to have the most amount of chain slippage, right? So it should be able to slip past each other faster than higher molecular. And we see this, that we have a very low, it's the lowest initial elongation to break. They can pull past each other and break. The higher molecular weights are a little bit better. That first, the data on this graph right here is 100% chain slippage. Okay, not anything to do with the nanocomposite. Look at how big an effect there is with just that little bit of nanocomposite. Okay, the bigger the molecular weight, you have a big, plate wants to slip past a large chain, is a higher effect than 2 long chains trying to slip past you. Now, it's going lower and lower elongation to break, but it's also increasing this. It's also increasing the tensile strength. Okay. So in this case here, what's really happening? Your material is getting more brittle, but it's getting more tough. It's not elongating as much. But if we look at our, you don't see the stress strain curve here, but it's getting harder to pull it. So this is hardening the material because of the molecular weight interaction with the thing. And it has less of an effect with the longer molecular weights. More effect with the lower molecular weights. Because they're slipping past the plates versus the chains. These shorter chains slip past those plates. The longer the chains are, the more of an effect because they slip past the plates. And they slip past the chain.
So looking at the graph, isn't LMW, isn't that the one that is most drastically affected by an increase in?
This is, yes, it is most drastically degraded by the MMT because the plates are breaking up. The short chains are not interacting with the plates enough, and they're just breaking apart. With the higher molecular weight, highest molecular weight, it's slowing it down, but the long chains are still slipping past each other. The plates are small enough that the chain dominance is greater than the chain to nanoparticle dominance. Did I say that backwards?
Maybe, I might have just misheard.
I might have said that backwards.
Okay.
But, so yeah, so the shorter ones are more affected by the plates because it disrupts the
It's interacting with less plates by nature of being short.
yeah, each individual polymer is interacting with fewer plates. Therefore, it is
Easier.
just break apart. So, yeah, so elongation is going down, it's getting tougher, but it's getting less elastic. Yes.
While there is no big difference between the MMW and HMW, and there is a lot of difference between the LMW and MMW, like the medium and low, it's high.
I suspect if you look at the chain length versus the aspect ratio of the plate, you'll see that these are much bigger, 2 to 5 times bigger than the plate lengths. This is getting closer to where the plate length is. And therefore, the chains are almost as long as the plates. So there's a bigger effect. I'm not sure, but I would suspect that is the reason.
And if you will see the test rate, it's like 0.5 centimeter per minute.
Mhm.
And it is like showing the abrupt behavior. It should be like, at the higher test rate, it should show the abrupt behavior. And on the opposite side, at the higher rate, it's showing the tactile behavior.
Oh, I see what you're talking about. Yeah, it's- at the slower test rate, it elongates more, even at the same deflection, versus the higher test rate.
Yeah.
So, no, that makes sense, because at the slower rate, it elongates more because at the higher strain rate, the more brittle it is, the faster it's going to break, right? So this is showing that this has a higher effect on the brittleness because the faster rate breaks faster at a lower load. Does that make sense? We're going to cover that in mechanical as well, but I just wanted to show that. I'll double check the reference on this. I think I missed something when I read it. Okay, so, and we've already seen this, that one of the reasons our platiness is really important in having that shear is we go from the big macroscopic particle to breaking it down into tactoids where all of the plates are aligned the same direction, but there's still that interfacial interaction between them. We have to either shear them apart, but then immediately, if they get next to another particle, another surface, they're going to immediately reorder. They're going to reorder them. So you have to have shear plus something to get in between. So we can do that with a small liquid polymer or a molten polymer. Either way, you have to get the shear plus some kind of breaking up of that interaction between the clay and the actual clay to clay platelet. Okay, and this works. I mean, this is clay, but it also has the same thing with graphene. Graphene wants to do the same thing. It wants to pi stack. why they use the graphene oxides to blow them apart. Okay, and so one of the interesting things about them is you can visually tell how well exfoliated something is because of light scattering. Okay, think about it. If you have lots of tactoids, each of those tactoids is going to scatter light because the refractive index is between the matrix and the particle, right? So the larger your particles are, the more different wavelengths of light they can interact with. Therefore, you're less dispersed, less well dispersed, actually ends up getting cloudier. Or if you have it even better dispersed. So this is exfoliated up at the top in a Dow resin. So exfoliated means the plates are completely taken off and separated out. Here, this is interpolated where the epoxy is just kind of pressed in between the plates, but there's still order. There's still some order, there's still a spacing. So exfoliated, imagine you have a wide angle electron scattering that says there's no order here, or bigger than 100 angstroms difference between the plate to plate. In interpolated, you're going to see that the plate to plate distance has gone from naturally occurring 5 angstroms to 25 angstroms. That's interpolating. You have polymer in between it, but there's still order. There's still plate to plate order. The difference between fully exfoliating and and that shows, yeah, the blowing up of that same structure. Notice that how the plate to plate order here. So this is more of interpolated. There's still the plate to plate order, but they're spaced further apart. Here we actually see fewer plates together, more plates dispersed. This is more indicative of what we would see for a fully exfoliated plating material. This is where we see an interpolated plating material. There's still that periodicity in the filler material. And then this is actually, once you've taken your nanomaterial, now you burn it out. You burn out the polymer. If you don't apply any shear forces, whatever that polymer or whatever that nanomaterial was, this is sort of kind of the structure it was when it was dispersed. It's not exactly because it had to give room for the gases to come out and stuff like that. But we see that it's burned out right here. And so there's some collapse of the three-dimensional structure. But you can see that it has a three-dimensional dispersion throughout the entire system. And again, this is thermally thermalized out of the material. And notice the scale here. We're not seeing individual plates. We are seeing aggregates of plates. Because this is 10 nanometers, so that means our individual plates can be, in this order of thickness, but a little bit here, we're probably seeing aggregates. And again, if you take this and squished it, it would go over.
This would come from exfoliator.
I don't know, because the thermal process can change that a little bit. Being that it seems to have a fairly open structure, it might be exfoliated because of having such seemingly open volume. But the fact that you have these things here.
That's why I'm asking. It seems like they're connected.
Right, they have the tendency to show the honeycomb structure after they are burned. Like for example, most of the materials will burn, they will show this kind of structure like honeycomb.
Because sometimes it's easier to see what the three-dimensional structure is after you burn it out, because TEM is only showing you one little thin sliver of your material. You really don't get a full picture of the three dimensions. So burning it out or doing some kind of micro X-ray kind of thing, giving you the three-dimensional structure, would give you a better indication. This gives you a better indication of the three-dimensional structure was in vectors. Because unless you're going to do TEM and then slice and TEM and slice, that's not all together. That's very practical experiment. But that's why I would do it. So. All right, and then, all right, hey. So in this case here, we're looking at, we can tell immediately on our system what we have. So this is what we, this is X-ray scattering. This is wide angle X-ray scattering. And so you start with, this right here is your solid surface, usually aluminum or something. And then as you come out, if you have an amorphous system, you're going to see that there's going to be no periodicity, no order. Okay, so this would be the line of maybe something fully exfoliated, so there's no order in the system. But you'll see there's a peak up there, and that peak equates to about 24 angstroms. So that means there's an intercalated material. Those plates are up on average 24 angstroms apart. Not perfect. See, it's not a single line, it's a line. Same thing happens here. We see that it starts with this it starts with having this completely dispersed amorphous, and we start seeing this peak coming in. And notice that peak is going further and further away. So we got some interpolation here, but the last peak there is twice the distance. Twice the distance. We've interpolated more material in between those plates, and it slowly walked over from our amorphous material all the way to our. Almost, it looks like it has twice the number of polymers between. Okay. And just trying to double check the thick line at the top is the 10% clay. The small line at the bottom is lower clay. So by the time you keep increasing the amount of clay you have, so it can disperse in the polymer, it can disperse in the polymer, it can disperse in the polymer. Now you've loaded it so high, the plates are starting to get close together. You're seeing those intervals. And this is that same line here. Yeah. So this is the same line here, where you start seeing at this one, it's even a lower loading, the 7.5. We're starting to see intercalates. And in this one, we actually start seeing intercalates even lower. We only get the lowest level, has no intercalates or very few. And then our intercalates form at a higher level. So this is telling us two things, that probably our maximum loading for this polymer is going to be at this 2.5. Maximum loading for this can go all the way to the sun. Just how well it is dispersed in the system. All right. And of course, I don't know what that is. That's a tribological thing. I don't know much about that. Okay, so I would like to stop here. It's 5 minutes early, but I'm going to stop here and stop recording. Stop share. And then on my next one,